So each of the alpha means older alpha or something, right?
Yes. And there will be multiple C to the alphas I will be defining here. There'll be regular C to the alpha, script C to the alpha, which are the ones I'll be defining shortly.
So, I mean, if it's differentiable and then derivative is bounded, then it's older, but this is a weaker thing, right?
Yes. Yes, that's correct.
It might not have a derivative. Yeah, then we're going into the case and it doesn't.
Yeah, exactly. Because if it has a derivative, you just take a Riemann-Stieltjes integral.
Jiggles around.
Jiggles too much.
Side these curves that come down.
Yes, exactly. So let me just remind you of the definition of rough path from yesterday.
That's why the alpha equals 1 is the critical thing, right? Because one of them is concave, the other one is convex. So that's when it switches.
Mm-hmm. Yes.
Convex one is the easy one, the concave one that's interesting.
Yes.
That's true.
Mm-hmm. Yes. So let me, definition, remind you. So given a signal, X in C alpha, so these are alpha holder on some time interval to RD. A rough path above X is a pair, or I would say is a map from the 2 simplex to a pair where first one's just a vector, second is a matrix, so that you have the following 3 things. X1 ST is X of T minus X of S. I just mean here, ST gets mapped to X1, X2, ST, ST. The second thing is a Euler condition on the second component. And then the third thing is Chen's relation, which is what we're going to be discussing today, which says that X2, T, X2, SU minus X2 UT is equal to, so SU1 times XUT1. So we're able to kind of split the second into the tensor product of the first order. And today I'm going to be talking about where Chen's relation comes from and also where these iterated integrals come from as well. So what was that? Oh, yeah. Thank you. So less than infinity. And then also here, I'm assuming this is for alpha in 1/3 to 1/2. Yeah, soup less than equal to infinity.
But the matrix one, isn't there?
We're on.
That's a matrix.
Yes.
So what does it matter what matrix?
That's the infinity.
Well, they're all equivalent, right?
Oh yeah. They just ask it to be less than.
Yeah, we just want it to be less than infinity, and they're all equivalent. Yeah.
So that's not that.
Okay, so E is not, that's is the matrix.
Yeah, that's right.
Yeah.
Yep. XST2 is a matrix, and you take any norm you want, and we just want this soup to be finite. No. And then the Chen's relation, I just wrote it down yesterday, didn't really mention where it came from. And today I'm going to talk about the work of Chen and where Chen's relation comes from. And it's going to relate it back to differential equations, I think, in a very explicit way. Yep. So actually, before I do that, let me just remind you what we do with the rough path. What we do with the rough path is the second order part, the x2 st. This turns into the integral from st, the integral from s to r2, dx of r1, dx of r2. In computations, I'm going to omit the O times there. Just keep in mind as a tensor product. And this is a definition where we write down what it is here. And then this double integral, this iterated integral here, is defined as the x2 part. Okay. So once we have that, then we can solve differential equations driven by x. All right. So I'm going to offer another explanation of where these iterated integrals come from than I did yesterday. And it'll also give you Chen's relation, why we want Chen's relation to hold. All right. So if we go back to just differential equations, the simplest differential equation we're interested in is going to be, so consider the differential equation for, consider x that's as smooth as you want, C infinity, dy, dt is equal to y, dx dt, with, say, some initial starting point y of s is equal to 1, okay? And here, this is a differential equation where x is smooth, as smooth as you need. Really, you would just need like C1 or something, but say C infinity. Now we can solve this differential equation. We get that y of t is x of t minus x of s. Okay. You just check that. Check that it satisfies it. You just take a derivative because everything here is smooth. All right. So one thing we can do with this solution is we can Taylor expand the x, right? So what happens when we Taylor expand x? We get 1 plus x of t minus x of s plus x of t minus x of s squared by 2 plus blah, blah, blah. And I'm writing everything in one dimension, but this also holds for x in any dimension. Now we can rewrite this here. Yeah, so it'll be you'll be squaring, you'll be taking this outer product. Yeah, so avoiding all of that, just think of this in one dimension for right now, just to see. And then this right here is equal to 1 plus, from s to t, dx of r, s to r2, t, dx of r1, dx of r2. So this is equal to the sum over all the iterated integrals of x. Okay, if x is smooth, you can just, these iterated integrals are just, you pull out an x prime, right? Okay. So if we're looking to solve differential equations driven by a smooth x, if we know all of the iterated integrals of x against itself, then we know the solution, right? So this is another way of talking about where the iterated integrals come from. And no. It comes from the integral. Yep, because each time you're getting out a 2 factorial, 3 factorial from the number of times you integrate, right? Yep. So that leads us to a definition of what is called a signature. So definition, the signature of a path given X, and at least for right now, let's just say it's C infinity. The signature is the collection of all iterated integrals. So I'm going to say the signature on ST, for example. So the collection 1 is to T dx of R, S to T dx of, ST S to R2 dx of R1, O times dx of R2 is the infinite collection of all iterated integrals. This is in what is called the tensor algebra over RD, which is just this direct sum of RD. It's okay. So it's just a scalar, a vector, a matrix, a cube, higher ordered. Okay. So that is the signature, and the signature comes from this solution map, right? And yeah, so I promised Serdar that I would not get too into any Lie theory here, but this is an exponential map. We can talk about Lie algebras, Lie groups. It's all very inherent here, but Serdar forbid me. So.
All space.
Mm-hmm.
Representative particle.
Yeah, and these iterated integrals come up in physics all the time. It's very, very common in physics, this collection of iterated integrals. All right, so now let's see if we can recover Chen's relation from this. All right. So going back to the differential equation, we have a multiplicative structure of the solution, right? So I had this starting at S for a reason. So this is really depending on both S and T, right? So let me just write YTS as the exponent of the increment. And this naturally satisfies this multiplicative structure of Y SU, YUT is YST, right? Just from the increments of X. What was that? Yeah, this should be yes. Sorry about that. Yep, so we're looking at the increment on TS, and it naturally satisfies this multiplicative structure. Okay, so the solution from time S to U and from U to T is just the solution from S to T, okay? And this translates to a relationship on the signature, because if you expand this out, you just get the signature, right? So this implies S, yes, exactly. I'm writing the Taylor series of this. Exactly. I'm writing the Taylor series as this product and just expanding everything out, right? So this just says that S, the signature on SU from UT, it's the signature from ST, and this is Chen's relation. That's Chen's relation. Then we can look at this product and then look at the varying stages of it to get the Chen's relation that I wrote for the rough path.
If we pull over the one goes with the two, 1/10 or 12, right? Some 10th or whatever. 8 feet, so Harvard was all the way up, right?
Yeah, that's right. But at, exactly, it's just for the second one. What I define in the rough path is just looking at the second component. And then, but this is for all orders. And this is true. This is literally true. And I'll just do a quick computation. Literally true if X is in C alpha, but we postulate that it's true if X is, we're not able to define X canonically, right? So let's just, let's just show what this is on first order, well, 0th order, first order, second order. So let's say we have SU is equal to 1, X1, SU, X2, SU, X3, SU, right? And same thing with UT, X1, now, if we just multiply everything out, the first one will be 1 equals 1, easy enough. Second one would be that XSU 1 plus XUT 1 is equal to X1 ST is the first order, which if it's an increment of a path, this is just true. Now for the second one, here's where it gets interesting is we, of course, so we have that guy multiplied by that guy multiplied by that guy, and these two are multiplied together. So we get X2 SU plus X2 UT plus X1 SU O times X1 UT. And we want that to equal to X2 ST. This is exactly the relationship that I defined for rough paths, right? And if you want, we can keep going. So for the rough path, I've just been talking about the order 2. And that corresponds to alpha between 1/3 and 1/2. But let's say you want to go down to alpha between 1/4 and 1/3. You can also write down all of these, which would just be X3 SU plus X3 UT plus X1 SU, X2 UT plus X2 SU times X1 UT is equal to X3 ST. And you can just keep on going and generating all of these more and more. And all of this is literally true if these iterated integrals are defined canonically. And I'll show that soon. And this is work done by Chen in the 50s, 60s, 70s. Very, very classical stuff, but It was about these iterated integrals. I mean, so when Chen was doing it, it did come up from solving these differential equations. That's one reason why people cared about it. But then also it just turned into, about Lie theory, really with rough paths. And I mean, with these iterated integrals, they're really taking values in a subset of the tensor algebra. It's going to be a Lie group and all this other stuff. So I don't want to get too much of Lie theory, but with some Lie theory, it was some differential equations and things like that. I mean, Chen had a bunch of papers on this, so it wasn't just one single thing motivating it, but yeah.
It seems like it's still expansion form is special. What if you have different differential equation, has a different solution, does not have that?
It's still going to be an exponential, actually. It's just going to be a more abstract exponential. So if you have the differential equation dy equals f of y dx, you still have an exponential map. It might not be something as clean or as simple as this, but it's still going to be an exponential map.
Definition in its Taylor expansion is all one. I mean, there's a factorial, but it's all one. So if you multiply these things together, one square is still one. So if it's a different coefficient.
Right, but then the exponential has the relation that e times e to the s, e to the t is e to the s plus t.
Right.
And your other function, who knows, right? It could be anything. There may be no relation.
Right, but the exponential flow satisfies that, right? The exponential flow, I mean, that's what it means. I mean, there's all this. Right. That's right. That's right. So it's going to be that. And then, as I said before, you get into all this Lie theory, which I guess I'm forbidden from talking about, but yeah. Sure. Yeah. Sure. Yeah, I wasn't planning on getting into it, but yeah, the point is with these differential equations, you're always going to have some kind of exponential behavior. It's going to be an exponential operator, exponentiating the f of y essentially, right? Yeah. So, I mean, I'm not sure what to say there. Yeah. But
it seems very specific to this exponential function. So if you have a different function, I was thinking you have different relationship between y and the f, and whether this argument will continue to hold there.
Well, if you had a different function there, I mean, you would have something different. But the point is, in the differential equations we're considering, we're always going to have an exponential type flow, right? It's always going to be some C naught semigroup, right? It's always going to be some kind of flow, right? Yeah. Yes. Yes. Yeah, that's right. Yeah. So let's just quickly verify the second order Chen's relation. Oh, yeah, go ahead.
What is in that equation? It's 2y dx. If there's 2 there, what do they have?
Well, it'll be yeah, what'll be, you just put a 2 in the exponent there, and then you get these iterated integrals multiplied by 2, right?
Then that's not left hand side is 4, but right hand side is 2.
Or however the constants work out, but you would have a constant, right?
They have a constant.
Yeah.
Oh, okay, okay.
So then you're just gonna have a constant,
Basically, hours of it, long video.
Very coefficient, that's what I.
yeah.
Difference gets scaled by the same number.
Mhm.
So you pull it all out in front of it, to have something tensor, you
Mhm.
will have a scale, you pull it all out.
Yes. Yes, that's right. So, yeah, let's just quickly verify this for a smooth path. Yeah, and actually, let me get to, I think, more at the heart of what you're asking is that, so the point is these iterated integrals serve as like a basis, right? It serves as a basis for a Taylor expansion. That's really the point of what's going on here is if we have another differential equation, we should be able to expand it out in terms of these iterated integrals. And you'll see this, for example, with the Wiener chaos expansion. So Wiener chaos expansion says if you're on Wiener space and you have an L2 random variable, then it can be uniquely expanded in terms of these iterated integrals of Brownian motion against itself, where the integrands are going to be the coefficients, right? So you really want to think of these iterated integrals as a basis for which you can expand other solutions. Right? Yeah. Exactly. That's exactly right. Yeah, that's exactly right. Yeah. So, yes, let me just. Mhm. That had to do with the fact that alpha was between 1/2 and 1/3. So if alpha was between 1/4 and 1/3, we'd have to have an x3. And if it was between 1/5 and 1/4, we'd have to have an x4. Because the point is, in the signature, because the decay term goes to 0. Or another way of looking at it is if we want to expand a solution in terms of these iterated integrals, well, once we take enough of them, then the Young theory holds, and then we can just canonically define the rest of the iterated integrals. But depending on how irregular the path is, you have to postulate more and more and more. Exactly, right? The first few have to be postulated in order for us to expand. And you really do want to think of this as kind of a Taylor expansion or some type of expansion in terms of these iterated integrals. Not to get too down this other rabbit hole of, so Martin Heirer had this extension of this called regularity structures, which is just a theory of expansions that came from a Taylor expansion, came from expansion as these iterated integrals. A regularity structure, if you've ever heard this before, is just a type of expansion. That's all it is. A Taylor expansion, an expansion of rough paths, an expansion in some form. Okay. So yes, let's verify this. Shouldn't be too hard, but it's good to see. So if x is in C infinity, we can just look at x prime of r dr minus s to u x of r minus x of s x prime of r dr minus from u to t x of r minus x of u x prime of r dr. So for this Chen's relation here, I just pulled everything over to one side, and I'm sure you guys can calculate integrals. The point here is that you have a xr and an x prime of r from s to t. You have xr, x prime of r from u to t, s to u. So that cancels out with those. And then after that, you can pull out the x of s. You can pull out the x of s here. You can pull out the x of u there. And then the integral of x prime from u to t is just, you can just evaluate everything and you end up just getting that this is equal to x of u minus x of s times x of t minus x of u. You just expand everything out. Good exercise to try that, writing out all the details, but there's nothing but just calculus. Okay. So Chen had showed just that Chen's relation holds for smooth paths, for iterated integrals of smooth paths inherently, right? You can just check by hand that it holds without anything fancy. Right. And for all orders, you just have to keep track of everything. But I mean, it's an algebra exercise, but there's nothing too deep going on. If you want to check this by hand. So the meaningful part was the exponent, right? Viewing it, viewing the exponential of the increment as a multiplicative functional. Yeah, there are things like that, shuffle products, things like that. Yeah. Right. Yeah, that's right. So I'm saying if we just define this for the actual iterated integral where x is in C infinity, so everything makes sense totally naturally, then all this just holds if x is a smooth path, right? And you don't even need it in C infinity. C1's good enough. I just wrote C infinity.
Or one, into one as prime or one.
Or I would, so that one.
So here you write the single integral because you have already solved that integral.
Yeah. Exactly. That's right. And then we can just write x prime because it's smooth. And then you just calculate everything out. That's right.
So use the old
If x is smooth, or you mean these objects?
Formally, put something in the integral, it's there, right?
Absolutely. Absolutely. And that's actually the
Then quickly, and you take one of those things and push it back down and make it a vector, right?
So the thing with rough paths is sort of you're algebraically defining something that's in the tensor algebra. You take something, or you have a path that takes values in this tensor algebra, and then you just postulate or algebraically define the second order part, and then you just call that the iterated integral.
You want to get out of this,
Yes.
push it down.
Yes.
Otherwise, it's living up in some symbolic space where we don't try and turn it into a number.
Right.
And you turn it into a number with
Yes. So it's it was what's called the rough integral, which is basically it's a Riemann integral plus some correction terms involving these iterated integrals. And then you can just turn it into a number.
question about the adding up the denominators. So it's above one. And
Yeah.
then so that you can do the young kind of integral then to turn it into some above a number.
Absolutely. And what you're describing is what I hope to prove soon is what is called the sewing lemma. So the sewing lemma just says that if you add enough of these extra terms so that the remainder is of order beta, where beta is greater than 1, similar to the Young theory, then you can just define this integral. It's really a similar argument as the Young integral, except now we just have to add extra terms so the remainder is higher. That's all. But that's exactly it. And the worse x is, the more of these terms you have to add. So I'm just sticking here mostly between 1/3 and 1/2, just because that is the easiest case. We only have to deal with one iterated integral, the second order term. but you can deal with as horrible as you want. You can deal with as arbitrarily low regularity if you can define these iterated integrals, which becomes a little bit tricky in lower and lower regularities. When you have like, so the hard part is going to be defining these iterated integrals. So actually, like I said, in one dimension, you can define an iterated integral like for any bad regularity just by x to the n by n factorial, right? That's a perfectly acceptable definition. But the problem is, how do you define the iterated integral of one component of the process against the other? That becomes tricky, especially when alpha is less than 1/4, it becomes really tricky in higher dimensions. So for example, for FVM with h less than 1/4, you can canonically define a rough path above it. However, h less than 1/4, you can define a rough path, but the rough path includes points outside of the interval. So it exists as a rough path in that it formally satisfies these definitions. It's somewhat unsatisfactory in that sense. So yes. I think there's a no-go theorem that you can't fix that. Yeah.
Perhaps see more detail of the problem.
Yes. So let me define some spaces. So one question that was asked yesterday was, all right, so the rough integral or the rough path above a signal is not uniquely defined, right? And so there's a couple questions. First of all, what kind of rough paths do we want? What are the nice rough paths that we want? What are the nice integration theories we want? Second of all, how do we even construct them? And both of these are answered by the same results. So let me just define some spaces here. I'm going to be using notation of Fritz Heirer, but there's all sorts of notations and all sorts of papers. So let me just talk about spaces. And it's going to be using this notation. Okay, so the first space I wanted to say was C alpha of 0t RD. So this normal C alpha are just alpha holder functions. So there is no so there is no second order part. These are just functions. Now let me define the space. Script C alpha, fancy, of say which would be the alpha holder rough paths. So the script alpha here, or sorry, the script C here is to denote the rough paths, not just the functions, right? And there's going to be two subsets of this.
Above, or what do you call above something in line above?
So I would say, given a signal, a rough path above that is going to be something. So this is including, so these are all the signals we're interested in. These are all the signals and all the rough paths above them.
Right. Start with something first line and say, give me a rough path above that. You take the collection of all possible rough paths over all possible signals.
Yes.
Yep.
Yes, exactly. However, this space of all possible rough paths over all possible signals is somewhat so there's some issues with it. So I haven't even defined a metric on this, but I will define a metric on this, but things like it's not separable. And there's some other issues with this. So we're really interested in what are called the space of geometric rough paths, these are the ones that we really care about. And as we were talking about yesterday, the lift above a path is non-unique. the geometric lift is unique, okay? So there's going to be two very closely related. They're going to be the space of weakly geometric rough paths and the space of geometric rough paths. So CG alpha is going to be the space of weakly geometric rough paths, and CG0 alpha is going to be the space of geometric So I'm going to define what a geometric rough path is. I'm going to define what a weakly geometric rough path is, but that is our goal. So let me start off with defining the space of geometric rough paths. So one thing to note is that there's a canonical embedding of C infinity into the space of alpha holder rough paths, right? So first note, I from C infinity to C alpha is canonical, right? You just take a smooth path to its iterated integral defined in Riemann-Stieltjes sense, right? And as we have just shown, this defines a rough path that satisfies Chen's relation, satisfies the Holder regularity. All right. And then we can define a metric on the space of rough paths, on the space of alpha holder rough paths. We define this metric. So given we define rho of this is our metric. Yep, C1 is enough here, right? Yeah, but so this is a metric, or sorry, it's not a metric. Should subtract off the Y. YST. There you go. So you take the difference of the components, and then you take the supremum over all T, and there should be another supremum here as well. We're taking the supremum in both of them and then adding, sorry. Yes. And yes, the important thing is that in the second part, you have a 2 alpha. In the first part, you just have a 1 alpha. If we had lower regularity paths, we would also have a third component and a 3 alpha, a fourth component and a 4 alpha, and so on. Okay. So then, what was that? That's correct. That's correct. And mhm.
Take one of them.
Mhm.
No limit.
It'll just be 0, right? Or you mean the second component? That's right.
The denominator blows up. That goes to
Right. So the numerator goes to 0 as well.
zero.
Yep, they both go to 0. That limit, I mean, it depends on the path. Well, it would be,
Derivatives. I mean, think of these, various generalizations of different food come in on a certain way and you get something.
sure.
Subject to the F also.
Yeah. So for a given rough path, I mean, you have this, for a given rough path, I mean, limit S T goes to S and whatever this is. I mean, it's always going to be zero, but we can talk about the behavior if you want. Yeah. Mhm. Yeah. Yeah. Once you have a fixed rough path. Yeah, that's right.
It's actually just a norm, right?
It is not a norm. Because C alpha is not a vector space. That's the important part, is C alpha is not a vector space. Right.
If it sits inside of another vector space, this is just a subspace, a subset of vector space.
Yes, it's a subset, and yeah.
The norm on the empty space.
Yep.
This is the points of the norm.
This is a manifold.
It is a manifold. Yep, it's a exactly. It is a manifold. That's right. So the space of geometric rough paths, what I wrote here is just the closure of C infinity in under this metric. So we define is equal to the closure of C infinity under rho. So it's going to be all the rough paths that we can approximate by smooth paths. And this is actually how you construct in a lot of ways. I mean, there's multiple ways of constructing, but this is the principal way of constructing a rough path above a signal. You approximate the signal by a sequence of smooth functions. Then you just take the limit with under this topology. Once you take the limit under this topology, then you get a rough path. And you can also show lines of Victoria, this extension theorem, that it is independent of the sequence of approximations, and all of this, you get a unique geometric lift to your rough path. And that's one thing I'm going to talk about soon, is how do you actually construct a rough path using, or a geometric rough path above a signal. Yep. So actually, one thing that I did want to prove at some point was what is called a Donskoy's theorem. So there's a rough Donskoy's theorem. So you can take a random walk, you can piecewise linearly interpolate it. You can enhance the that with the standard Riemann-Stieltjes integral, and then Donskoy's theorem for rough paths shows that this weakly converges on the space of rough paths to Brownian motion enhanced with a Stratonovich integral. So that's one thing. That's one proof that I did want to give soon. So you were so you're asking about like what does this metric look like for a Stratonovich? You just write this out. I mean, one thing that's hard to do with that is it is done pathwise. So you're given a particular instance of a Brownian motion and a particular integral here, right? And then you just take the supremum of it. So you could take the you could just set y equals to 0, and then you get basically the norm, which isn't quite a norm, but you could just look at it. I don't know if there's anything too interesting there, but the thing that I think is interesting would be this rough version of Donskoy's theorem. And this is generally speaking, this Donskoy's idea is generally speaking how you construct rough paths. The idea is that you do some kind of smoothing process then you enhance it canonically, then you take the limit and you end up with a rough path, right? And it's independent of what exact smoothing you do. Yes.
After every 3 tenths of so on.
Exactly. Exactly, right? And you just keep getting low, you keep getting more and more of these, the lower regularity you are. But like I said, the hard part is defining a rough path above a signal for, like, say, H less than a fourth or for alpha less than a fourth can become quite tricky and can become very unnatural, even if they do exist. So let me just, so I already mentioned Lyon's Victoria extension theorem, proved in 2007, basically saying you can construct a rough path above any signal with alpha between 1/3 and 1/2. Let me just write a little bit about what are called the weakly geometric rough paths. And this is another important class of rough paths. So this is geometric, and then the weakly geometric is the ones where you have basically either an integration by parts or a chain rule. Okay, so weakly geometric, so we say is weakly geometric if symmetric part of X2 ST, which is equal to X2 ST transpose is equal to that. In particular, what this says about the diagonals is that X2 II is equal to XI, sorry, X1 II ST over 2. So the weakly geometric are the ones that satisfy this relation, which basically implies an integration by parts or implies a chain rule. So the geometric or the weakly geometric would be the Stratonovich integral over a Brownian motion. Because the Stratonovich integral of Brownian motion integrating against itself is just b squared by 2. The Ito integral is not geometric or weakly geometric because you don't have this. Squared, that's right. Yes, thank you. It should be squared by 2. Yep. And one really important thing is that geometric implies weakly geometric. And sort of the other way around. You lose a little bit of regularity if you want to go the other way around. But basically these are the same. A geometric rough path is the limit in the rough topology of a sequence of smooth paths. So geometric rough path is the space of geometric rough paths is the closure under the rough topology of all the smooth paths.
In a sense, with all the fixed outcome, that's how you define the 0 alpha G. All those grow and grow.
Yes.
In this case, the way you define the form doesn't seem to have any alpha dependence.
That's right.
You have the alpha set up to begin with. So when you go this way, you are alpha by the
Yeah. So if you're weakly geometric if you're alpha holder rough path, that's weakly geometric, then you are geometric with your beta holder geometric for all beta less than alpha. Yeah, I mean, this is a very similar idea to if you do Komarov continuity criterion, you always lose that epsilon. And if you look at the proof, of some of this stuff, it'll look very similar to Komarov continuity criterion, things like that. And you just lose a tiny bit. Also, one thing that is really nice is that these embeddings are actually compact. So that's a very useful thing that we, when I go to prove Donskoy's theorem, we can use the compact embedding.
I didn't understand that two comma line.
Oh, sorry, that should just be one I.
Okay, well then, okay, I don't understand what those I's after the two mean.
Oh, so this is just a matrix, right? Yeah, this is just a matrix, right? So that would be X2. Yeah, so just the diagonal term. That's what the geometric thing says, is that the diagonal term is just the square divided by 2 of the increment of the process. So that would be like the Stratinovich integral and other ones like that. Yes.
What was right now?
It's just another rough path. It's a perfectly acceptable lift. It's a perfectly valid rough path. It's just not geometric, nor is it weakly geometric. Well, the thing is, remember the F, you can always add the F, right? So an Ito integral is just going to be the Stratinovich integral plus 1/2 t or minus 1/2 t, right? And that's the F here. The F is just the increment of 1/2 t. So you know, the point here is that you can construct a geometric rough path. And then if you want another rough path for another purpose, like if you want the Ito rough path, then you're always able to just add on whatever function you want to it. The point though is we can construct a geometric one, which is unique. And then we can add the F, and these are all acceptable definitions. They might not be geometric, but we can just add and subtract F. It's not quite bounded variation. It would be 2 alpha, but yeah. So the F would be the increment of a 2 alpha function. So if we're between 1/3 and 1/2, it's not quite bounded variation, but it's you know, within the Young theory at least.
Doesn't make the rock to.
Exactly. Yeah. So you're always able to add that part. The hard part is constructing the geometric. That's where that's where all the work actually is constructing a geometric rough path above as given signal. Once you have that, then you can construct all the other ones just by adding the F.
Find that F to make it weakly
Sure. I mean, yeah, that's a good question, right? So if you're just given some generic rough path, well, what you can do is you can just look at this, right? You can look at this and then just subtract off this part. And then whatever is left over is going to be the thing you have to remove, right?
It's not hard to find a geometric one. It's hard to find one rough path.
Yes. It's not hard to find a geometric, it's hard to find any rough path, right? The hard part is to find any rough path above your signal. Once you have one rough path, then you can just add and subtract these Fs and you can get the geometric, you can get all the ones that you want, but the hard part is finding any rough path above it. So geometric, it basically comes down to the geometry of like, this here is a fundamental theorem of calculus, right? This is saying that this behaves the same way. So it comes down to, if you're interested in, I think the terminology comes from, if you have rough paths that are taking values in some manifold or some geometric space, this is going to be the one you want. So for example, if you're doing stochastic calculus on some manifold, generally people stick to the Stratanovich just because change of coordinates makes it a lot easier under change of coordinates. The geometric one is the one that you can do and have the change of coordinates, you know, a lot nicer. But that's generally where it comes from. When I was first learning this, I had the same question, and I was trying to figure out, does this have to do something with like a geometric series or something like that? No, it's just comes down to geometry in terms of spaces. All right.